Hello everybody. We're going to look at the error analysis that follows from your measuring the height of the ceiling using the fall of the lacrosse ball. We're going to take the lesson that you learned from the tutorial and apply it here for each of the three main types of uncertainty in any measurement. That's instrument uncertainty, systematic error, and random error. We're going to apply it to each of your three measurements: time, mass, and weight. Because this is critical in any lab. When you make measurements, you don't know those measurements perfectly. And if you use those measurements to calculate something else, then you got to show how that uncertainty propagates throughout. So we're going to learn this and apply it over two separate videos. So the first one is going to apply to your error analysis, a page where we're going to quantify, keyword there, quantify, assign numbers to each of your uncertainty to each of your measurements. I'll be referring back to your data table. Even though I don't have data, I'll help you fill in some of those blanks that you couldn't get from your original measurements. Okay, so let's take each measurement. Let's take the most important measurement for this lab in getting accurate idea of the height, and that's your time. That's the most difficult one, and that's the one we're going to focus most on because that's where all your error came in. So there's three sources of potential error that comes in timing. There's measurement error, there's random error, and then there's systematic. Measurement error and random error are the easiest to quantify, and you will almost always have to do that in a lab. Systematic error is more difficult, but it's something we definitely need to talk about for timing, because if we do timing labs again, you want to learn from this. Okay, so measurement error, that comes from the device you used. I'm assuming you use a digital stopwatch, probably from your phone. So there's rules for that. You have a digital device. So if you recall from the notes, in a digital device, your uncertainty is simply the smallest value you can record on that device. So if you have a stopwatch that measures out to the hundredths of a second, which I'm assuming yours does, then the best you can say is I know something to the hundredth of a second. In other words, 0.01. The rule for an analog device where you have markings on there is slightly different. You can always go half of the smallest value, but you can't do that with digital. So if you go back to your data table, right here is where you always record your uncertainty from the instrument. So this is the measurement time. So delta t doesn't mean change in t, it means uncertainty in t, and that's plus or minus 0.01 seconds. Okay. Now you're going to have a bunch of other times in here. You don't fill this in, right? And I'm going to come back to something else later. All right, I won't fill in the rest. So there is instrument uncertainty. Next uncertainty you have to look at is random error. Random error comes from you doing multiple trials. I doubt very much that for all 10 trials you got the exact same time, even though in theory the ball should have dropped for the same time. You have a spread in data. So there's a very simple formula we're going to use anytime we do multiple trials in a lab to see how much spread there is. And that's, again, random error. And I'm not going to go into math, but since we have less than 10 measurements, we can use this simple equation. If you had a lot of measurements, which is more ideal, you would use a fancier statistical technique called standard deviation. But we don't have to do that for this class. So this is a really important equation. We saw it in the notes. So I label random error as the uncertainty in the average time. So note that I put delta t average, whereas the instrument error was simply delta t, the measurement. So that's the maximum time minus minimum time divided by 2. So if I go back to my hypothetical data, and let's say I only have 6 data points, my random error would be my biggest time, 0.81, minus my smallest time, 0.54. Whoops. And divided by 2. So I'm not going to work out the math there, but actually maybe I should. So this is 0.27 on top divided by 2, which is 0.135. But the important thing is I don't want to leave it like this. I want to round that to about 0.1 second. So I want you to do the same thing with your data. In this space right here, put your max minus min divided by 2, and then round that to 1 sig fig, and then go back and fill that value in your data table. In other words, I just have one blank for that. It's a very large blank. but that's your random error. So let me put this in perspective. If my average time from these 6 was, let's say, 0.65 seconds, and my random error is, let me just leave it as 0.13, I have a fairly significant amount of error here. 0.13 is about 1/5 of 0.65, so that's 20% uncertainty. I didn't make my times I don't know very well, and that's a definitely source of improvement if I were to do a later lab. Okay, so take care of that. You can leave this as to the nearest hundredths place. I'm not going to worry about rounding to 1 sig fig. I changed my mind on that. Sorry about that. Okay, so the last type of uncertainty that we need to look at is the most difficult to quantify. And you're not going to have to quantify it here, but you want to think about it. And so that comes from continuously doing the wrong thing. Okay, and with timing, it usually means either starting too late, starting too soon, stopping too late, stopping too soon, and doing that consistently. And I'm going to guess, all right, if I were to look at all the individual trials, right, let's say I had 20 students in a section, I would say 15 are going to have times that are too short. You have a systematically stopping the stopwatch too soon. You're anticipating. So we want to learn how to get around that. But let's break down the different aspects of timing. Normally, if you were doing this in a lab, you would have 2 people, someone dropping, someone timing. Okay, so I was dropping, you were following me, and then you determine when to start and stop the stopwatch. So let's look at how the following might affect it. So let's say I just abruptly dropped it in the video. I didn't give you any warning, and then you started the stopwatch. How would that affect your timing? Would you be on time? Would you start too soon or too late? Okay, so if I abruptly drop it, you're probably going to start it too late, right? You're going to start the stopwatch a fraction of a second after I drop it. So if we do that continuously, you're systematically going to be off in time, perhaps. Now, a way I can get around it is countdown to stop. I can go 3, 2, 1, drop. Idea behind that is you could be on time, but I can see too soon. Sometimes we anticipate, and that's a big issue. Now, let's talk about when you stop the stopwatch. So the obvious way might be, I'll look to see when it hits the ground. Okay? So that can go one of 2 ways, I think. The obvious way is if you wait and then press the button, you're going to be too late, right? There's a reaction time. What happens more often is you anticipate. You don't like the idea of being too late. You kind of anticipate, I'm going to be too late, so I want to stop it sooner, so you stop it too soon. So I'm not worried about what you circle here, but this is what really happens. This is what you think would happen. Okay, so how do I get around that anticipation part right here? Well, a really good technique, if it works, and I don't think it'll work in the video, is to close your eyes and just listen to when it hits. So you listen, then you stop the stopwatch. So it's hard to anticipate, even though people still do it, because again, it's like an innate thing not to want to be late. So that would make it too late, in theory, right? I hear it, I react, I stop, it's too late. You might say, well, why would I want to do that if it's going to be too late? Well, I'll point out something in a minute. Now, another way you can do it, and this is maybe perhaps the best way, is to have the same person start or drop it and time it. So I could hold the ball in one hand and have the stopwatch in the other hand. And so when I start it, it's really easy to be on time. I can coordinate the release of the ball with the pressing of the button. The stopping, well, that depends on what technique I do. That's really hard to do. If I'm looking for it, I'm probably going to be too soon. If I listen, I might be too late. Okay, in theory, I can maybe be on time. So what I'm trying to get at here is there's no one way to best do it, but here's my suggestions. Either go this route and work at it, or do the following. So let's say someone's dropping and another person's timing. Have the person abruptly drop, so you're too late on your stopwatch. And then listen to when it stops, and so you're too late. So if you're late in starting and late in finishing, that will probably offset each other, and you'll get a more accurate time. Okay, as odd as that may sound. You'll have more, hopefully, experiences to practice this. So let's move on to our other measurements. Okay, so you have 2 other measurements to help you measure the height of the ceiling or calculate the height of the ceiling. Next measurement let's take is mass. Okay, so we got to go through the three types of error: measurement, random, and systematic again. So what device did you use to measure mass? You used an electronic balance. Electronic balance is digital. Our scale only went out to 1/10 of a gram. So our rule for digital, it's 1/10 of a gram. That's the best we can do. So if I go back to our data table, or below the data table, then where it says plus or minus, put 0.1 gram. In other words, your mass of tape, I don't remember what it was, let's say it was 54.6, plus or minus 1. Notice I want these two to match each other in terms of level of precision. So when you go to kilograms, right, that would become 0.0001 kilograms. That's a little awkward. It might be better to say 1 times 10 to the negative 4, but I'm not going to worry about that right now. Okay, in terms of random error, what would be the random error in our mass? The answer is there is none. So why is there no random error? Or recall, random error comes from the spread in multiple measurements. Well, you didn't do multiple measurements because you only measured once. It doesn't make sense to put the lacrosse ball on the balance 10 times. You might have 10 different lacrosse balls and put them on there to get multiple trials, and then you could do a random error. Okay, systematic error. What's a possible source of systematic error? So if we go back to the notes, and this is something you have to be aware of, especially with mass or weight, is zeroing issues. In other words, when there was nothing on the balance, did it read 0? Well, if you go back and look at the video, it did read 0, so we're going to be pretty confident that we weren't under or over measuring it because of zeroing issues. All right, last measurement, we'll finish up here, is the weight. Okay, so the measurement error on that. If you look back at the video at the actual scale on there, I believe that the smallest measurement was 1/10 of a Newton. The smallest marking again is 1/10 of a Newton, and if you read it properly using the rules that you were taught earlier, you should always go one place beyond that. In other words, your weights here should have been to the 100th of a Newton. You could have gone that precise. So since our smallest marking is 1/10, we can say that our uncertainty is half that value, or 0.05. Okay, so again, the spring scale is an analog device, so you can always go one place beyond. Since our smallest marking was 1/10 of a Newton, we can go to half of that and be fairly confident. Okay, again, there's no random error because one measurement. All right, and systematic error, possible source. This is definitely more of a concern than with an electronic balance, but you saw at the beginning when we were measuring hanging the ball from the scale, I had to zero it, right? I had to turn that little screw at the top to get the plunger at 0. So there's potential zeroing, but we try to take care of that. Okay, so that's it for the systematic error. These are things you have to consider for the labs we do where we have all these measurements. So if you have any questions, make sure you ask. Because the next thing we're going to do in the next video is we're going to look at propagation of error. And this is a little bit more complicated, but it takes all those uncertainties that we just quantified and sees how it affects ultimately our calculation for the height. Okay.